Hello and welcome to LFI Educates. After the conclusions were made in alpha-ray scattering experiment by Rutherford, he presented the planetary model of the atom, or we call it as nuclear model of the atom. Let me write down here Rutherford's nuclear model or we call it as planetary model of the atom or of an atom. Let us see one by one. The first point, he says that every atom consists of a central core called the nucleus. Every atom will have a central core. That central core we call it as the nucleus. In which the whole positive charge and the entire mass is concentrated, in which the entire mass and entire positive charge is concentrated. That we call it as the nucleus of an atom. Point number 2, the nucleus of an atom is of the order 10 to the power minus 15 meter, he says, which is very much small as compared to the size of an atom. As compared to the size of an atom, which is around 10 to the power minus 10 meter. So the size of the nucleus is very, very small, it says. The third point, he says that an atom is electrically neutral. The number of electrons that are outside the nucleus and the number of protons, the positive charge inside the nucleus, both must be equal. The number of electrons outside the nucleus and the number of protons in the nucleus are equal. This was the third point in Rutherford's planetary model of the atom. And as you look here, planetary model, planet, we know that planets go around the sun. So that example you can take it and keep in mind the fourth point. Electrons revolve around the nucleus just as the planets revolve around the sun. So these are the few points according to Rutherford, the model of the atom or the structure of the atom. Let us see some few terms related to alpha particle scattering experiment. The first one that we are going to see is distance of closest approach. We write it as R naught. Let us see what it is. Suppose this is the nucleus of an atom, and then one alpha particle is heading towards the nucleus. This is your alpha particle, is heading towards the nucleus. Now when the alpha particle is moving towards the nucleus, the distance, the kinetic energy with which it is moving, as we know, kinetic energy is energy possessed by a body by virtue of its motion. So if alpha particle is heading this side, that means surely it has kinetic energy. This alpha particle, when it is moving towards the nucleus, the kinetic energy of the alpha particle will become lesser and lesser, and then at some certain stage it will become zero. The kinetic energy of the particle will become zero, because we know that alpha particles are positively charged. Now this kinetic energy, what happens to it? By the law of conservation of energy, this kinetic energy becoming lesser and lesser. Why is it becoming lesser? Because positive, they are like charges, so they will repel each other. So the velocity with which the alpha particle will move will become slow and slow, or in other words we can say that this kinetic energy will become lesser and lesser, and then that kinetic energy will be slowly and slowly getting converted into electrostatic potential energy. Suppose here it has reached the alpha particle. This distance, which it cannot go any further closer to it, from here the repulsion will take place. If it is coming straight, as you know, it will go back. If it is coming a little bit down here like this, it will be deflected. This distance, we call it as the distance or distance of closest approach. We write it as R naught. That means lesser than this distance, it cannot go further. The alpha particle cannot go further towards the nucleus. This is your nucleus. So at a distance of closest approach, the whole kinetic energy gets converted into electrostatic potential energy. So it gets converted from one form to another form at a least distance of closest approach. Now electrostatic potential energy, as you have studied in electrostatics in chapter 1, chapter 2, that it is given by 1 by 4 pi epsilon naught. Charge of alpha particle, it is 2 times plus 2e, and charge of the nucleus Ze divided by distance, the least distance. Now when the alpha particle has reached there, it is R naught. This will give you an expression. Kinetic energy, if you write it as K is equal to this one. K you can write it as 1 by 4 pi epsilon naught 2 Z square. E into E you can multiply E square divided by R naught. And this R naught, if you cross multiply here, you will get 1 by 4 pi epsilon naught 2 Z square divided by K, the kinetic energy. Or you can even write this as R naught is equal to 1 by 4 pi epsilon naught 2 Z square divided by kinetic energy formula, all of you know, half of mv square. Like this. Or in terms of K also you can write like this. You can calculate the distance of closest approach. Here the terms that we have used, 2E is charge of, or we'll write plus 2E charge of alpha particle. Ze is the charge of nucleus. Z indicates the atomic number. And here mv square is mass of alpha particle and v is the velocity of alpha particle. And m indicates mass of alpha particle and v indicates the velocity of alpha particle. Here what you can look very carefully is this distance of closest approach is inversely proportional to kinetic energy. So if kinetic energy is more, then the distance of closest approach will become less. That means if this kinetic energy of alpha particle is more, then R naught will become less, will come closer to the nucleus. And if the kinetic energy is less, then it cannot go very near to the nucleus. The distance of closest approach will become more. So it entirely depends upon the kinetic energy of the alpha particle. Distance of closest approach depends upon the kinetic energy of alpha particle. Now let us see one more term, impact parameter. We write it as B. It is the perpendicular distance. Let me draw here, then it will become more clear. Nucleus plus ZE. This is the central line. Suppose one alpha particle with plus 2E is approaching with velocity v. Then this distance, the perpendicular distance of this velocity vector from the central line will give you the impact parameter. Now this impact parameter, you cannot take it when it is close to the nucleus. It should be far away from the nucleus. It depends upon this angle. This is your alpha ray trajectory or alpha particle trajectory. Trajectory is the path through which the alpha particle deviates or diverts or goes. It is the perpendicular distance of the velocity vector of alpha particle from the central line when the alpha particle is far from the nucleus. Here is far from the nucleus. Rutherford derived the expression for impact parameter. You don't have to derive it, you need to know the formula. Mathematically, Rutherford derived the impact parameter like this. B is equal to 1 by 4 pi. B indicates the impact parameter. 1 by 4 pi epsilon naught Z E square cot theta by 2 divided by the kinetic energy, or we write it as half of mu or mv square. So this is the expression for this is half of mv square. Like this also you can write. This expression gives us two things. It depends upon the impact parameter, depends upon this angle theta. It depends upon this angle theta. What is theta? Then you know by now. It's called the scattering angle. By how much it got scattered. Now, case 1. If B is large, cot theta by 2 also will become large, as they are directly proportional to each other. Now if cot theta by 2 is big, then theta will become very small. Look here, if this impact parameter will become large, suppose here is the alpha particle, then the value of cot theta will become large, overall theta will become very, very less. In that case, the alpha particle will just pass straight. The angle theta, this impact, this scattering angle will become very, very less, it says. I think it is clear. Now, the second case, case 2, if B is equal to 0, the impact parameter suppose it is 0. Then cot theta by 2 also will become 0. Then cot theta by 2 also will become 0. Now cot theta by 2 0. Cot theta by 2, when it is 0 it is 90 degree. Cot 90 degree is equal to 0. We can write like this, cot 90 degree. Now in such a case, if you remove cot from both the sides, theta by 2 is equal to 90 degree. Then here theta will become 2 into 90 is 180 degree. So if this impact parameter is 0, that means the alpha particle is here moving in this horizontal line, then the scattering angle you can see it will become 180 degree. Then it has to go, before striking the nucleus, it has to come back. It cannot reach up to the nucleus, it has to come back. The angle made, this scattering angle will become 180 degree. It will go like this and then it will come back. And we know that along with this line it was trying to move. This angle will become 180 degree. Suppose the nucleus is situated here. Then it will go and come back. Then angle made with this horizontal line is 180 degree. So it will get retraced back along its own path. Now let us see about the drawbacks of Rutherford's model of the atom. Now let us discuss about the electron orbits. Rutherford's model of the atom gives us a clear picture that the electrons are revolving around the nucleus, and the whole mass or the entire mass and the entire positive charge is concentrated at the central core of the atom, and that central core we call it as the nucleus. Now if an electron revolves around the nucleus, if it takes a circular path, then the electrostatic force between the electron and the nucleus, the electrostatic force will provide the necessary centripetal force to keep hold of the electron that is revolving around the nucleus. So this centripetal force and this electrostatic force both will be equal in such a case for a stable orbit. Let us take an example of hydrogen atom or H atom. If I write, you can understand. Now anything or any object that goes around a circular path, you have learned in mechanics that it possesses centripetal force. The object will have centripetal force, and that force is directed towards the center of the circular path. Now the centripetal force expression, as you have learned, is mv squared divided by r. Then the electrostatic force between the electron and the nucleus of hydrogen atom. Now we are taking for hydrogen atom, it will be 1 by 4 pi epsilon naught charge of electron E into charge of the nucleus ZE divided by the radius of the orbit. We will take it as r, as we have taken here r, that is r square will come here, the force of by Coulomb's law we are getting it. But for hydrogen atom, you can write here like this: E is the charge of, E is the charge of electron, ZE is the charge of nucleus. But for hydrogen atom, we know that Z, the atomic number here, Z indicates the atomic number, Z is the atomic number. Now for hydrogen atom, we know that it will become Z square divided by, or Z for hydrogen atom, we know that for hydrogen atom Z is equal to 1. So if it is 1, then it will become E square divided by R square. One R you can cancel it. Then you can get the expression for radius is 1 by 4 pi epsilon naught E square divided by mv square will come down, mv square. So from here you can find out the velocity with which the electrons are revolving in around the nucleus, as well as the radius. If I draw it here, ZE, this is your nucleus, this is your electron, this is the radius, and this is the velocity with which it is moving around the circular path. You can get the expression like this. Now if we want to know the energy at which the electrons are revolving around the nucleus, that also we can calculate it. The kinetic energy we can find out like this: kinetic energy is equal to half of mv square. This is half of mv square. You can see from here mv square is equal to 1 by 4 pi epsilon naught E square divided by R. So this will give you 1 by 8 times 2 4s are 8 pi epsilon naught E square divided by R. Together also you can write like this. Let it be equation number 1. Then let us calculate the potential energy, because mechanical energy is the sum of kinetic energy as well as potential energy. So potential energy, to find out, potential energy is equal to electrostatic potential energy. You know the formula already. P is equal to 1 by 4 pi epsilon naught. Here magnitude of charge, electrons are negatively charged. You have to keep in mind that left to right. Z is 1. So for hydrogen atom we are doing, or for time being I will just write down minus P into Z divided by distance is R. This is the expression for potential energy. This one you will get like this. Potential energy we can write as U. U is used for potential energy. Kinetic energy we use K. Potential energy we use U. It's not V, it is U. So you can write this one as minus Z is 1. So minus E square, or 1 by 4 pi epsilon naught is 1 by 4 pi epsilon naught. Z is 1, so E square by R. E square by R. So this one we can mark as equation number 2 with a negative sign. Here one minus will come. It's very essential to know. This one will be minus. Potential energy will come out as negative. So therefore mechanical energy will be sum of kinetic energy plus potential energy. If you add these two, you will come to know the energy with which the electrons are revolving around the nucleus according to Rutherford's model of the atom. And let us put the values. Kinetic energy here you can see 1 will not write. E square by 8 pi epsilon naught R. E square by 8 pi epsilon naught R. And potential energy is negative. Is minus of E square divided by 4 pi epsilon naught R. So plus into minus, you do minus. Mechanical energy is equal to, if you take LCM, you will get there 8 pi epsilon naught R. This will become E square minus 4. 2 times is 8, so 2 E square. Ultimately it will become minus E square divided by 8 pi epsilon naught R. This is the mechanical energy of the electron when the electron is revolving around a nucleus according to Rutherford's model of the atom. You may see here why it is negative. Mechanical energy is here negative. It shows that if the energy is negative, it is holding. That means they have force of attraction. It is holding. If electron will have positive energy, then it will fly away tangentially. This nucleus cannot hold the electron. It will fly away tangentially. Here negative sign shows that there is force of attraction between the electron and the nucleus. If force is if mechanical energy is positive, the electron will get detached from the nucleus, and if it gets detached from the nucleus, then atom will not exist. Now let us see the drawbacks of Rutherford's model of the atom. Drawbacks of Rutherford's model of the atom. The first one, let us see. According to classical electromagnetic theory, if a charged particle revolves around another charged particle, like your nucleus is your charged particle, positively charged, and then this is your electron, this is also negative, this is also charged particle, negatively charged particle. If a charged particle revolves around another charged particle, then it should emit radiations of all frequencies. Now if it emits radiation, then slowly and slowly the size of the electron or the mass of the electron should become lesser and lesser, and slowly the pull of the nucleus will become more and more, and it should fall into the nucleus. That is your first drawback of Rutherford's model of the atom. If it emits radiation of all frequencies, then the electron must spiral and then fall into the nucleus. And if the electron spirals like this and falls into the nucleus, then atom will not exist. So this was the major drawback of Rutherford's model of the atom. This is regarding the stability of the atom. So he could not explain the stability of the atom, we can say in other words. Again, I repeat it once more. If an electron, a charged particle, revolves around another charged particle, then it must emit radiation, like a candle. If you burn a candle, it emits radiation, it gives us light. Then in turn, the candle becomes shorter and shorter. The mass of the candle becomes lesser and lesser. That is here also, if the mass of the electron becomes lesser and lesser, then the pull of the nucleus, because it is positively charged, positive and negative, they will pull each other. So the pull will become more and more, and if the pull becomes more and more, then ultimately it will fall in the nucleus and the atom will not exist. This is the first drawback of Rutherford's model of the atom. Now when you come to the second drawback, it could not explain regarding the formation of line spectra. Hydrogen or atoms, they produce line spectra, not continuous spectra. You can see here, if the electron spirals and comes like this, and then it falls into the nucleus, the radius of the electron with the nucleus becomes lesser and lesser as time passes by. This radius is becoming lesser and lesser. Earlier it was this much big radius, then it became small, then it becomes smaller, again it becomes the smallest. So if the radius will keep on changing, radius will become lesser and lesser. continuously it is emitting radiation. Continuously, if it emits radiation, then it must give us continuous spectra. Like we discussed about V, I, B, G, Y, O, R. Then our rainbow, when you see V, I, B, G, Y, O, R. Suppose this is violet, this patch is violet, indigo, blue, green, yellow, orange and red. This type of spectra we call it as continuous spectra. One after the other color, they are compressed together. Like this type of spectra should be observed even in atoms, especially in hydrogen atom. Now when we talk about the spectra, it was found out that hydrogen atom does not give us continuous spectra like this. It gives us line spectra. Line spectra is like this. One colored light, if you see here, then big gap, and after that the next colored light, and a big gap or a little bit maybe small gap like this. But they are not continuous. Gaps are produced between them. So this type of spectrum is observed in hydrogen. We'll be discussing later on the five different types of line spectra that you get in hydrogen atom. So Rutherford's model of the atom could not explain the formation of line spectra as well. According to him, it should have been like this, continuous spectra. But in actual practice, we see line spectra, and why line spectra is produced, he could not explain. So here, the drawbacks, the difficulties faced in Rutherford's model of the atom. Later on, these two things, the stability of the atom and the formation of line spectra, was explained in Bohr's model of the atom. Thank you and have a nice day. In the next video, we'll study about Bohr's model of the atom.